Yes, okay. Thank you. The title is How Green Chemistry Roots Help to Fabricate N-type Organic Semiconductor for the Transistor Construction. First of all, I wish to tell to all of you greetings from Romania, where I come from, and many thanks for invitation to organizer and to participants to this 50th edition of the Green Chemistry and Renewable Energy Conference in Rome, Italy. Thank you very much. Where I come from Romania, maybe a few words, few pictures are interesting to see you. We are in Europe, and here you can find the mountains and the Black Sea and the winters, as you see, and also the castle of Dracula, if you have the opportunity to visit us. I live and I work in Bucharest, the capital of Romania, where you are welcome with next occasion that you would have. I work in a university from Bucharest, Politehnica University, with a longer name, National Polytechnic University of Science and Technology from Bucharest. And as some special point, I'm working electronics. Here we have a Faculty of Electronics and Telecommunication. I work in microelectronics, the Department of Electronic Devices and Circuits, but I work in electronic devices that deal also with the materials for electronic devices. The outline of my presentation go to introduction in the topic. Then I will tell you a few details about SSA, NSC. What it means, this sulfosalicylic acid with nanocore shell nanomaterials as properties. I will call it shorter SSA, sulfosalicylic acid, because this is the core of the nowadays presentation. Then the characterization of SSA, and then how we produce a test transistor to set up the technology, and then how we measured some static characteristics, and few particularities and discussions. Few words about introduction in the actual state of the art of the industry of organic semiconductors. Successful materials used in organic semiconductors are today the semiconductor used are pentasene, tetrasene, and other. They are based on the molecular conjugation. That means alternance between single and double chemical covalent bonds. They are based on these materials. Traditional are based on polycyclic aromatic hydrocarbons (PAH) as precursors, and they unfortunately present carcinogenic potential during processing. In general, PAH composed present multiple aromatic rings. Pentasenes, for instance, present 5, tetrasenes 4, etc. So we use these materials today for fabrication of OTFT, organic thin film transistor. They are transistor with very thin film, thickness about less than 1 micrometers, about hundreds or tens of nanometers, and the composition of films are based on organic materials. Where are used these transistors? In color, excuse me, in color display, in mobile phones, in transducer for biosensor, as you see in the picture. Here are the chemical shape of pentasene and tetrasene, as you see, with more aromatic rings. In history of the organic semiconductor, P-type, so meaning working with holes, the p-types organic semiconductors were firstly produced. And the polymers with small molecules such as pentacene are used for the p-type organic semiconductor, while the n-type transistors are very poor represented. Today, still can be used pentacene to produce n-type, but only in very special and expensive conditions, like, for instance, range for the temperature go very low to almost 0 Kelvin. No 0, but 500 kilo Kelvin degree. That is not usual for normal use of a transistor. So we still continue to find out the alternative and other materials for N-type organic semiconductor. Besides to this, of difficult properties of manipulation, the toxicity of polyaromatic hydrocarbons are present and still exist. As you see, here are few papers and publications that give details about the toxicity of this polyaromatic PAH, who include also traditional, like pentacene. The lethal dose 50 is around 10 to 19 micrograms per kilograms. So green materials are necessary and useful to obtain green environment, and that is useful also for people who work in the clean room and in microelectronics factory. As we have a previous expertise, we applied, we construct synthesized nanocore shell materials with doped materials by external shell using PABA, para-aminobenzoic acid, to construct organic semiconductor. PABA nanocore shell offered p-type semiconductor behavior, and the transistor adopt a typical configuration of an organic transistor, but it is normal. We use the configuration of point contact, usually named pseudo-MOS transistor, for testing. The device was prepared by silver deposition on a glass substrate, followed by deep coating deposition for the organic materials. And then we measured static characteristic that have, here is the proof. By measuring this static characteristic, we have to prove the acceptor behavior of this film for the p-type. That meaning an accumulation onset conducted by negative gate voltage. Green technology, how they help the microelectronics industry. The usual organic technology are cheaper, in general, organic technology are cheaper than the silicon technology, because the processings happen here at room temperature or very close to the room temperature. By printing, by deep coating, that don't need high temperature as in silicon, that need, maybe 1000 Celsius degree. Then the nanocomposites advantage consists in a high surface volume aspect ratio that also that allows the induced charge segregation. So nanocore shell are suitable. Investigations of these semiconductors without toxic configuration, in particular, you see the previous papers that report also carcinogenic effects. Combining in this way nanocore shell with external organic shell is a recent domain and useful in the film transistor fabrication. For our materials, it is true the world expression, there is no poison, but is a dose. So we expect also to have for nanocore shell a dose of toxicity, but if we find that this lethal dose LD550 will be much higher for nanocore shell, the result this materials are more green than previous used. What literature say? They used also nanoparticle, but made by cobalt and mangan nanocore, and they used polyaniline as external shell, producing N-type semiconductor with a large band gap, 2.3 electron volts, carrier concentration 4 to 10 to 16, applied in photovoltaic cells that practically are photodiodes, as you see. So how we produced these SSA materials? In the category of green compounds also enter the ferrite nanocore shell materials, which represent for electronic device already represent an intrinsic semiconductor matrix. So only NSA with the core of ferrite is an intrinsic semiconductor behavior. Previously, we attached to this nanocore shell para-aminobenzoic acids organic molecule, and respecting the molecular conjugation, and we obtained p-type semiconductor. Now, we attached sulfosalicylic acid as organic compounds, and we have to prove that we offer N-type semiconductor. The NSA is magnetic nanocore material that is indexed also as a semiconductor with a Fermi energy of 3.64 electron volts, large band gap, 2.2 electron volts. So the magnetic core shell play a significant role as a matrix for intrinsic behavior of semiconductor, like that is similar like silicon. Pure silicon is firstly a semiconductor with a poor and a large semiconductor band and with a poor carrier concentration, but then after we add impurities or in this case of organic, after we attached the organic molecules, the semiconductor become more conductive, become proper for application in transistors. Here is a chemical structure of the sulfosalicylic acid. As you see, it contains only one aromatic cycle and a sulfonate group. Here we use the simulation of this molecule to have a first clue that it could present N-type behavior. How we synthesized these materials? Materials were performed by acquisition from Sigma Aldrich materials, components, chemicals, and we used ferrite chloride, ferrosulfate heptahydride, sodium hydroxide, sulfosalicylic acid, acetinonitrile as solvent, and we using ultra pure water 18 to 2 mega ohm per centimeter we used in all washing and solution preparation. When I say we, I am a microelectronist and I work together for this synthesis with a colleague, another professor from organic chemistry department. And here we work together. The nanoparticles were prepared from ferrite primary ferrite nanocore particle, and the solution is presented in this picture in the left corner. Here is chemical concentration of each substance you see in this slide, and the quantities and the succession of the chemical reaction are established by my collaborator, professor of organic chemistry, and you see here the practically the prescription to obtain the materials. Then the SSA materials was characterized by simulations and by TEM imaging. Here is the first proof of the behavior as N-type materials of SSA. The molecule was simulated by HyperChem molecular modeling programs, and it indicates the electric charge distribution. All the values that are present in these pictures are normalized at the electron concentration. And as you see, if you, for instance, if we make the algebraical sum for all values of this electrical charge, the molecule gives 0 coulombs, 0 electrical charge. But as you see, there is a brace of the molecule that present minus 0.3 approximately, this normalized charge that behave like an excess of electrons in this region. And it will be true that the measurement will prove this electron enhancement of the material. Also, the three-dimensional molecular simulations were made in this picture. The sulfonate group processed was proved to set a negative electronic charge as exact density of minus 0.298. So sulfosalicylic acid seems to be a donor of electrons, and in this way we expect to have electron as majority carrier in this material. Also, because these molecules are surround the nano particle of ferrite, here are another kind of simulations. The SSA nanoparticles distributions modeling in the volume of liquid made by three-dimensional modeling software TOMVIS. Here you can see what you can see. For instance, a nanoparticle is this green with core, yellow core and red core, and you can estimate the size of a nanoparticle around, as you see in these pictures, around 20 nanometers. And also you can estimate the distance between two nanoparticles. Is this material's nanocore shell of magnetite having the external shell of sulfosalicylic acid, is this a low toxicity materials? For the SSA sulfosalicylic part of this molecule, we can observe that is a veritable green compound that is encountered in the nature. It is act in plants as plant hormones or vascular drug. Obviously, as I said before, here also could be concentrations that can, if they are applied more concentrations that natural and normal, that can become a poison, but we will extract this immediately. The lethal dose for sulfosalicylic acid reported in literature, we don't calculate it, the reported lethal dose for SSA was 700 milligram per kilogram, while the lethal dose for polyaromatic hydrocarbons are 20 microgram per kilogram. So much higher quantity of this green plant hormone could be touched in by a human body or plant or anything from nature, and are not dangerous. The other part of the molecule, ferrite, magnetite, has also a low toxicity because why? By degradation, it can generate ions of iron and oxygen. And iron and oxygen are also are usually encountered in the human body and in environment. This SSA compound is, however, much more green compound for organic electronics than polyaromatic hydrocarbons. Also, considering the characterization of these materials, you see here some transmission electron microscopy TEM image of the synthesized ferrite nanoparticles, to which you see the ferrite nanoparticles, for instance, in this picture, as a dark region, black dark region, and you can also observe on the edge of this dark, you can observe the external shell of sulfosalicylic acid molecule that were attached to the external shell. Also, you can estimate now, not by simulation, by measuring, by TEM, the size of a nanoparticle around 10 nanometers. Also, for characterization of this substance, we use the dynamic light scattering DLS analysis, and the result of the apparatus is given here, that extract the zeta potential and the other parameters that you see in these pictures. So after this apparatus measurement, we can tell that the average hydrodynamic diameter is 50 nanometers. We obtain a good uniformity proved by the polydispersity index value that you see is 0.187, a very good dispersion stability according to the zeta potential. So zeta potential 45 millivolt prove a very good dispersion stability. To be stable, an organic compound is very important because in the down of the organic semiconductor producing, many authors reported sometimes good organic semiconductors as electrical properties, but with a lifetime about few days, few weeks, and then few months. So our compound is stable for a few years. That is very good. Test transistor technology and setup. We start with indium tin oxide coated glass substrate purchased from Bruker Daltonics from Germany, and then polystyrene 200 nanometers as organic insulator was deposited onto the ito face by deep coating methods. Then the solution of ferrite sulfosalicylic acid was deposited as an upper film, 400 nanometer thickness was optimum thickness onto this polystyrene film by deep coating using 90 millimeters per minute extraction rate for deep coating. The organic film thicknesses are estimated by the light reflection in ultraviolet visible spectrum. Then the electrodes, the source, drain, and gate a source drain by aluminum, gate by silver, were probes placed on the chip under microscope using the pseudo-MOS transistor also configuration as you see in this picture. So the conceptual structure of a pseudo-MOS transistor is in the left side. We have the glass covered by ito, covered by polystyrene, and then over polystyrene we have the ferrite SSA organic materials. We put on this film two top contacts representing the source and the drain under microscope, and we contact the ito, that is practically the bottom contact, as the gate terminal. And in the right side you see the configuration under microscope. Here you see different variants of structure that can be transformed in pseudo-MOS transistor that were performed. The upper are using ito materials, and the bottom used the silver. We tried also using silver instead ito, but ito was proved to be the best. Okay, could be problems during this. What problems could appear during these measurements? Scratching of the film, because if we put here some probes on this few hundreds nanometers that you see is still transparent, so thin it is transparent, the film, as you see here. The yellow part of the lamella is yellow. There is the sulfosalicylic nanoparticles. So we can produce the scratching of the film by probe. If the scratch are so deep so that they completely remove the organic semiconductor is bad. And to avoid this, we learn to all the time checking by probe measuring, and we learn to control the probe pressure. If the pressure don't completely scratch and remove the film, the source drain resistance must measure tens mega ohms by Hameg multimeter that we have for measurement to indicate no accidental penetration of the probe through the film occurs. For the source drain contacts, we have used this micropositioner, and also in the bottom you see we tried to construct variants with the deposition of some top drain and source contacts, multiple contacts, to use them from time to time. But they belong to different structure and strategies to study this material. Here are the principal work of the nanocore shell sulfosalicylic transistor based on the pseudo-MOS configuration. Practically the pseudo-MOS configuration in a cross section look like in this picture. We have C film for pseudo-MOS. We have usually C film, silicon film, N-type, for instance, placed on an insulator, and under insulator we have the substrates that are usually also silicon. This substrate practically contacted bottom behave like a huge contact representing the gate contact, the bottom gate contact, and on the top of the film are placed the source S and the drain D contacts. When we apply, as you see in this picture, with red and with blue, when we apply a positive gate voltage positive, we attract electrons from silicon N-type. N-type is rich in electron. and if we apply the positive gate voltage, this voltage attract electron. We produce in this case the accumulation regime for this transistor. And with red color, if we apply negative gate voltage, we reject electron. We reject electron, and after the rejection appears this plus in circle that are the ions, the positive ions of the impurities. And if we insist and we apply Vg negative less than a Vt, V threshold voltage, we can also attract holes at the bottom of the film. And in the right picture, you can observe the standard characteristics drain current versus the gate voltage in inversion and in accumulation with red and with blue. This is a principle that have to be respected in a pseudo-MOS transistor. And now we replace silicon and other insulator with our organic compounds. You see here the transistor that was biased under a double stabilized power supply, HAMEG instruments, and the drain current were recorded by a Keithley picoampere meter. The source was grounded, and the drain and the gate electrode were independently biased. So what static characteristic we measured for this transistor? As you see, if we, in the left side, we obtain the first image, we firstly increase the gate voltage toward positive values to prove the existence of electrons in our film. And if we obtain this increasing of the current with the positive gate voltage, we observe the enhancement of the current for a stronger positive gate voltage that is in agreement with the accumulation of electrons. That is the second proof after the molecular simulation. This is the second proof of the N-type behavior of this film. Here in the right picture are some comparisons between our measurements and some measurements of other N-type organic semiconductors reported in literature, not this material. Output characteristics are those that report the dependence of drain current, but now versus the drain source voltage, VDS. Here we have to obtain an increasing followed by a saturation of the current to have the behavior of transistor, to prove that these materials are useful to obtain a characteristic for a transistor. So we obtained for different gate voltage, as you see, 5, 10, 15 voltage, we obtain a family of output characteristics that present an increasing region of current with VDS that represent the quasi-linear regime. And then after saturation voltage, the current tends to saturate, as in a transistor, normal transistor working mode. And now few particularities and discussions concerning these measurements. For the static characteristics, we observed if we keep the probes on the film, and if we continue the measurement along the time, we observed that at different minutes and seconds, as you see here, we recorded in 200 seconds what happened. We observed that the drain voltage and at a drain, the drain current for a drain voltage equal to think 1 volt here, and two curves are for different VGS, 1 and 5 volt, suffer of instabilities in time. And explanations could be, after another discussions, could be due to the percolation effect in these materials, nanocore, with nanoparticles. Another particularities is drain current depends on the geometrical aspect factor. Fg, you see, is the usual for any transistor, is double V, the the width of the transistor on the length of the transistor, multiplied by mobility and multiplied by specific capacity of the insulator. So all the geometrical factors are included in this Fg. And for different length channel L of our pseudo-MOS transistor, 1 millimeters to 3 millimeters, we obtained, as you see, different characteristics. It is normal to be like this. Another observations that improved our measurements, we are searching a solution to reduce the oscillation in time of the characteristics. And if we apply the thermal treatment at 80 degrees Celsius, we obtained alleviation of these instabilities systematically. So the transistor with the length of 3 millimeters tends to keep the increasing of the current with the voltage applied, gate voltage applied on the bottom structure. And we can observe also here are the characteristics, drain current versus gate voltage, but the curves are recorded at different time. If the voltage are changed and then measured after T1, 1 second, 5 seconds, 20 seconds, we obtain these different curves. However, the average increasing happen in any situations, and the characteristics are much stable now. Also, we studied for these transistors the dynamic behavior of the transistor. And here you observe the study with an oscilloscope of the amplification of the signal. For instance, a small signal of low frequency 10 kilohertz was applied on the gate. So the gate represents the input of this device regarded as an amplifier of signal. And you see the little sinusoid, and then the amplified signal recorded in the drain of the device present good amplifications. So the device also, from the dynamic point of view, amplify the input signal usually that is applied on the gate. In conclusions, synthesis of nanocore shell sulfosalicylic acid under the green nanotechnologies, because we used these green roots from the chemistry, were performed. The microphysical characterization provide a good stability, and the core of ferrite has 15 nanometers, while adding the external sulfosalicylic shell, the nanoparticles reach 30 nanometer or around this value. sometimes 50 nanometers. The molecular simulations proved the polarity as N-type of the nanocore shell sulfosalicylic nanoparticles. The technology of deposition of organics SSA over polystyrene organic insulator was performed by self-assembling nanotechnology and deep coating, using practically deep coating method. And solid structure of organic thin film transistor with top contact and back gate type was produced. Finally, the method characteristics prove an N-type behavior of the film, and the threshold voltage of 8 volt, in agreement with the positive range and in agreement with in general values of organic N-type semiconductors. Ratio in the ratio of the current in the state on off is 100, close to the parameters of a classical pentasyn organic transistor. And we have to take the advantage that toxicity of nanocore shell is much less than the toxicity of the pentasyn, as you see in the repeated values put here. So this was our work. Thank you very much for your attention, and I am ready for questions from your side. Thank you very much.